All right. Hi, my name's Taggert Barton. I'm a student at BYU, studying Chem 105 right now, and I made a quick little presentation on gas laws. This is based off of the textbook for the class, titled Chemistry: An Atoms-Focused Approach, third edition, focusing on chapter 9, sections 4 to 6. So yeah, here we go. If I can go to the next slide. Okay, so the first part I'm going to focus on is relating the different parts of the gas laws, which are pressure, temperature, and volume, and moles as well. I should have included that. So I'm going to go through the different laws that relate these different factors of gas, which are Boyle's law, Charles's law, Avogadro's law, and Montan's law. So first off, Boyle's law. His law focuses on relating pressure and volume. So this is basically the principle that, so kind of saying it again, the principle that the volume of a fixed quantity of gas as a constant temperature is inversely proportional to its pressure. So if you look here on that second bullet point, pressure, that sign is a sign for proportionality. So it's inversely proportional to volume, or pressure is proportional to the inverse of volume at a constant temperature and moles of gas. And then we can use this equation down below in the third point, which basically allows you to solve for a missing variable of pressure or volume if the temperature and number of moles is constant for the gas. So that is pressure 1 times volume 1 is equal to pressure 2 times volume 2. So the next law is Charles's law, which relates volume and temperature. So I'll read this again. Principle that the volume of a fixed quantity of gas at a constant pressure is directly proportional to its absolute temperature. So volume is directly proportional to temperature at a constant pressure and moles of gas. And then this is kind of the same idea with this equation at the third bullet point, solving for a missing variable if you have one. So if you have, say, an initial volume, then a final volume, and then a final temperature, but you're missing your initial temperature, and you have constant pressure and constant moles of the gas, you can solve for that initial temperature. So that's volume 1 divided by temperature 1 is equal to volume 2 divided by temperature. And as you go through 2, you can manipulate this equation so you can solve easier for the missing variable. Next law is Avogadro's law, which is relating pressure and number of moles. So I'll read this right here. Top, it says, principle that the volume of a gas at a constant temperature and pressure is proportional to the quantity or moles of the gas. So this is relating pressure and moles. They're directly proportional at a constant temperature and volume of gas. And then here's the equation that you can use to solve for a missing variable. So it's volume 1 over number of moles 1 is equal to volume 2 divided by the number of moles 2. And then lastly, Montan's law, which relates pressure and temperature. So reading the description of it, it's the principle that the temperature of a fixed quantity of gas is proportional to its absolute temperature if its volume does not change. So pressure is directly proportional to temperature at a constant volume and constant moles of gas. And then here's the same idea with the equation at the third bullet point. Pressure 1 divided by temperature 1 is equal to pressure 2 divided by temperature 2. So we'll do a quick practice problem. There are many more practice problems you could do with all these different laws. I'm just going to do one of them and focus on one of the laws. But going through it, several students at a northern New England college are hosting a party celebrating the mid-January start of spring semester classes. They decide to decorate the front door of their apartment building with party balloons. The air in the inflated balloons is initially 21 degrees Celsius or 7 degrees Fahrenheit, about. After an hour outside, the temperature of the balloon is negative 24 degrees Celsius or negative 12 degrees Fahrenheit, very cold. If we assume that no air leaks from the balloons and that the temperature in them does not change significantly, how much does their volume change? Express your answer as a percentage of the initial volume. So what are we working with here? We have the initial temperature, which is 21 degrees Celsius. And then we have the final temperature, which is negative 24 degrees Celsius. And we know that there are no air leaks, so the moles of air is going to be constant, and that the pressure doesn't change, so the pressure is going to be constant as well. And then in here, we're asked to solve for a percentage of the initial volume. So we actually don't need a final or initial volume. We can just, we'll basically use Charles's law, because that law relates volume and temperature, and that's kind of what we're working with. So Charles's law, if we're using that equation that we start with, volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. We'll manipulate that equation so it's easier to solve for that percentage of the initial volume. Or here, let me make sure I'm saying that. Yeah, percentage of the initial volume. So V1 over V2 is equal to, or volume 1 over volume 2 is equal to temperature 1 over temperature 2. And an important thing to note is when we're using these equations, we always convert our temperature to Kelvin. So the conversion for that is degrees Celsius plus 273.15 is equal to Kelvin. You can also shorten it to 273, but I like to be a little bit more exact. So 273.15. And then we'll label each one as each volume and temperature in the equation as either final or initial. So it's kind of backwards and confusing. I should have switched this, but we'll do volume 1 as the final volume. Volume 2 as the initial volume is equal to temperature 1 as the final temperature, and temperature 2 as the initial temperature. And you'll see that V1 corresponds to T1, V2 corresponds to T2. So V1 final is going to be T1 final, and T1 final are going to be, they're going to be final, or V1 and T1 are going to be finals, and then V2 and T2 are going to be initials. It doesn't matter which is which, you can change. So volume 1 could be an initial, and then T1 could be an initial because they're both 1. So they'll both correspond to each other. And then V2 and T2 could be finals, if that makes sense. But we'll work with this equation. And then, so we can solve for the percent of our initial volume. And we have the initial as our denominator in this because it's percent of our initial. And then we'll have the final as our numerator. And then we basically plug in the temperatures that we converted to Kelvin. So negative 24 degrees Celsius, you can see down here at the bottom, negative 24 degrees Celsius plus 273.15 is a conversion. That will convert to Kelvin. That divided by 21 degrees Celsius, which was our final temperature, plus 273.15, that converts to Kelvin, is equal to, and then as it's converted to Kelvin, 249.15 Kelvin, which is our final temperature, divided by 294.15 Kelvin, which is our initial, and we get about 0.84702. So put that as a percentage, that's 84.702%, and that is our percentage of our initial volume. So I hope that made sense. With these questions, I got these straight from the book, which is, I don't know, not very creative on my part, but they're good questions. They're good practicing. So if you want more practice, just go straight to the book. And I have a reference for the book at the end of these slides. And then next section, section 5 in chapter 9, talks about the combined gas law, which basically puts all these laws together. Actually, the next section puts them together even more, but this puts 2 different laws together. So just defining what the combined gas law is. It's the principle that the ratio pressure times volume divided by temperature for a given quantity of gas is constant. So we'll combine Boyles's law and Amonton's law, which, if you remember, Boyles's law says that pressure is inversely proportional to volume, and then Amonton's law says that pressure is directly proportional to temperature. So we combine those laws with those equations that we have, and we get pressure 1 here at the bottom. Pressure 1 times volume 1 divided by temperature 1 is equal to pressure 2 times volume 2 divided by temperature 2 at a constant number of moles. So we'll do another quick practice problem with the combined gas law. I'll just go ahead and read the question. This is also from the book in section 9.5. But it says the pressure inside a weather balloon as it is released is 789 millimeters of mercury. That's just units of pressure, same as standard atmospheres or pascals. And and then it says, if the volume and temperature of the balloon are 131 liters and 20 degrees Celsius, what is the volume of the balloon when it reaches an altitude where its internal pressure is 235 millimeters of mercury and the temperature is equal to negative 52 degrees Celsius? So what are we working with? So we have the initial pressure, which is 789 millimeters of mercury. And then the volume and temperature of the balloon are 131 liters and 20 degrees Celsius. So those are our initial volumes and temperature. So what is the volume? So we're going to solve for volume of the balloon when it reaches the altitude, when it reaches an altitude where its pressure is 235 millimeters of mercury and the temperature is negative 52 degrees Celsius. So we're going to set up this equation, and we're going to, the combined gas equation, and we're going to solve for volume. So first we can convert our Celsius temperatures to Kelvin. So our initial temperature, 20 degrees Celsius plus 273.15 is equal to 293.15 Kelvin. And then our second temperature, our final temperature, is negative 52 degrees Celsius plus 273.15, which is equal to 221.15 Kelvin. And then we have our combined gas equation, which says that that equal sign should be a proportional sign. But this equation works. It works. Equals. So P1 times V1, pressure 1 times volume 1 divided by temperature 1 is equal to pressure 2 times volume 2 divided by temperature 2 at a constant number of moles. And we know that the moles didn't change. Yeah, it doesn't say necessarily, but the moles didn't change. So that's constant. So we'll rewrite the equation so we're able to solve for the missing volume. So with some mathematical manipulation, we get volume 2 is equal to, so that's the final volume, is equal to volume 1 times pressure 1 times temperature 2 divided by temperature 1 times pressure 2. And then we basically plug everything in. So volume 2, so the final volume is equal to 131 liters times, so that's our initial volume, times, and then I just did the initial pressure divided by the final pressure. So 789 millimeters of mercury divided by 235 millimeters of mercury times, and then the final temperature divided by the initial temperature, which is 221.15 Kelvin divided by 293.15 Kelvin. And then we plug that into our calculator and we get 331.8 liters. Yeah, so hopefully that made sense. And then the last section, section 6, deals with ideal gases and the ideal gas law. So this goes a step further and includes moles basically. But to define an ideal gas is a gas whose behavior is predicted by the linear relations defined by the combined gas law. So when we combine ideal gas expressions, so basically all those different gas laws, we get pressure is proportional to the number of moles times the temperature times the inverse of volume, or pressure is equal to a constant variable or a constant universal, some sort of constant universal gas variable times the number of moles times temperature times the inverse of volume. And then we get our equation, which is pressure times volume is equal to number of moles times R times temperature. And R is just a variable used to express the universal gas constant, which I'll go over in the next slide. But so yeah, PV equals nRT. And the way I kind of remember that, our teacher kind of talked about it in class, but it kind of sounds like pervnert, which kind of sounds like pervert if you like read it across, PV nRT. So I don't know if that helps, but it helps me. So that's the ideal gas equation. And then going a little bit further into that, so the ideal gas law or ideal gas equation is a principle relating the pressure, volume, number of moles, and temperature of an ideal gas expressed by the equation PV equals nRT or pervnert, where R is the universal gas constant. And R, there's a whole history behind that, but I won't go deep into that in this video. But R is equal to 8.314 meters cubed, pascals per mole Kelvin. And then you can manipulate the units used in this for this variable, for this universal gas constant. So the number might change, but it's essentially the same. So you could manipulate the units. So it's 8.314 liters, kilopascals per mole Kelvin, or you can manipulate it as 0.8206 liters standard atmospheres per mole Kelvin. And then the product of volume and pressure represents the work that the gas does when it expands against opposing pressure. So here at the bottom, we can see that, so this is basically putting energy into that gas constant. So this is just a reminder, energy is basically the ability to do work. So if we were to manipulate this a little bit more, we see in these upper values how meters cubed times pascals. So that's or liters times kilopascals, or liter times standard atmospheres. That's volume times pressure. Meters cubed, meters cubed and liters are units of volume, and pascals and standard atmospheres are units of pressure. So volume times pressure is the ability to do work, which is energy. So we can rewrite the units as 8.314 joules per mole Kelvin. And joules are a measurement of energy. So good to know. And then just a quick thing that the section went over about standard temperature and pressure, or STP, which is basically defined here in the United States as 0 degrees Celsius and 1 ATM, or 1 standard atmosphere. And yeah, so if it gives you a problem, or any if you get like a problem that you have to do, and it tells you that tells you that it's at standard temperature and pressure, you know that it's at 0 degrees Celsius and 1 standard atmosphere. So we'll do, this will be our last little thing we'll do, just a quick practice problem with ideal gas laws. And again, you can find more practice problems in the book that I'm taking basically all this from, and it's very helpful. But I'll go ahead and read the problem. So bottles of compressed oxygen carried by climbers ascending Mount Everest contain 1 kilogram of the gas. O2 is oxygen. It's a diatomic molecule. So it's oxygen is just written as O2. It doesn't exist just as oxygen. It exists as O2 in the atmosphere. Fun fact for you. And then the next part, what volume of oxygen can one bottle of oxygen can one bottle, oh, this must be, I must have put this in. What volume of oxygen can one bottle deliver of oxygen deliver to a climber at an altitude where the temperature is negative 38 degrees Celsius and the atmospheric pressure is 0.35 standard atmospheres? So what do we have here? We have that a climber ascending Mount Everest has 1 kilogram of gas. So, you have 1 kilogram of oxygen. You're looking for the volume of oxygen in one bottle that one bottle can deliver at an altitude where the temperature is negative 38 degrees Celsius. You have your temperature, and and the pressure, so is 0.35 standard atmospheres. So you have your pressure. So we'll go ahead and use those, and we'll use the ideal gas law ideal gas equation, and then we can solve. But there are a few things we have to do with this equation that might make it a little tricky. It's just a few extra steps. So we can use this equation. Pressure times volume equals number of moles times universal gas constant, or R, times temperature, to solve for the volume. So we're not given the number of moles, which was the tricky thing. We were given how the mass of the gas used of oxygen, but we can find the molar mass of O2 of oxygen, which is basically adding up. If you go to the periodic table, the molar mass of oxygen is 15.999 grams per mole. And if you round that, 16 grams per mole. And then you add 2 oxygens together because it's a diatomic molecule, you get 32 grams per mole, which is the molar mass. And then you can use that to solve basically for the number of moles that you have for oxygen. So you convert kilograms to grams, because you want to keep the number of units the same in that equation, so that way you're not getting the wrong number of units. That makes sense. So you have 1,000 grams. So 1 kilogram converts to 1,000 grams times, and then you want to keep the same. You want to basically cancel out the grams. So it's 1,000 grams times, and then you invert the molar mass of this. So it's grams per mole, but now it'll be mole per grams. So 1,000 grams times 1 mole per 32 grams. So that's the molar mass of O2. And basically the grams cancel out when you multiply it that way, and you're left with moles. So it's 1,000 grams times 1 mole of oxygen of O2 divided by 32 grams of O2 is equal to, and you solve that, you get 31.25 moles of oxygen or O2. And then you have your moles, and you have the temperature, you have the pressure, and you already know the universal gas constant. So you just plug them all in, you solve for volume. So volume, and you can manipulate the equation like we've done before. So volume equals number of moles times R, universal gas constant, times temperature divided by pressure. And then you plug all that in. So you get 31.25 moles, what we got here, of oxygen, times, and then for this universal gas constant, it has to agree with all the units you are using in this equation. So we know we're using standard atmospheres. We know we're using moles, we're using Kelvin, and we're going to solve for liters in this case, because did it specifically ask for liters? I just asked for the volume. So with this, we already have this value for the universal gas constant, solves for liters. So we know our end result, our end solution with volume is going to be in units of liters because of this universal gas constant. So back in previous slides, we know that universal gas constant if we're using standard atmospheres, moles, and Kelvin, we're going to solve for liters. It's 0.8206. Oh, that's actually wrong. It's 0.0286. I'm very sorry about that. That is the wrong value. I need to fix that. I made this really quick, so please forgive me. 0.0826, plug that in, 31.25 times 0.08206, that's universal gas constant, times, and then you convert your temperature to Kelvin. So negative 38 degrees Celsius plus 273.15, that gives you the total amount for Kelvin. And then you divide all that by the pressure, which is 0.35 standard atmospheres. And then you get your answer. You plug that in the calculator, solve it out. 1.723 times 10 to the third liters. And that's your answer, solving for volume. But yeah, do keep that in mind. Universal gas constant is not 0.8206, it's 0.08206. So yeah, remember that. Yeah, and that's it. That's my reference to the book. And thank you so much for watching. Hope you hope you understood and learned something. Thank you.